All right, what we have here is a fairly standard example of a two moving bodies style of application. We have a lot of pieces of information that at 2 p.m. the runner leaves. The runner is going at 10 miles per hour, and at 2:30 p.m. the driver leaves, and that the car is traveling at 55 miles per hour. What we're interested in knowing is how much time it will take for the driver to reach the runner. So if we think about this is going north, so let's just say that here's their house. Assuming that we start from a house. I know you're all envious of my drawing abilities now. Let's put some smoke coming out of the chimney because after all it's Texas, so it's probably freezing cold right now. We're in both cases going north. We have a person. We have a car. They both go north. They both leave at the same time. They both leave from the same place. And when they have caught up, they are also both at the same place, right? So here's our little picture of what's going on. Anytime we have a two moving bodies problem, and this could be either two separate moving bodies, or it could be maybe a car or a boat going in two different trips. We want to set up a table for the distance, rate, and time of each of those two moving bodies. So we're going to say we have a runner and we have a car, and each of them has a distance, a rate, and a time. Let's do the easy stuff first, right? So if we make a little table here, maybe we can make it look kind of fancy. Put some dividers in here. Do the easiest stuff first. So the runner is running at 10 miles per hour. That is a rate. And the car is traveling at 55 miles per hour. That's also a rate. Now that we've put these numbers in, we know what units we're using. That rate is in miles per hour. And the only way for that to work is if my distance is in miles and my time is in hours. So I have to be very cautious about this. Now, I don't know the exact amount of time either of them is moving, and I also don't know the distance. So this is where some variables are going to have to come in. But I am given a little bit of information about those times. It looks like we are given some explicit information about time, and we're not given any explicit information about distance. So that's a clue that that's where I might want to look next. Now, this is a little tricky. The runner leaves at 2 o'clock p.m. The car leaves at 2:30. I don't actually care what time it is. What I care is how long was the runner moving compared to how long the car was moving. If the car left later, then the car was traveling for less time. Somehow the 2:30 being a bigger number than the 2 o'clock sometimes gets people thinking backwards about this. But here's what I'm going to do. I'm going to call X the car's time. And the reason I am choosing that as X instead of the runner is just because, well, maybe I've done this problem before, but looking at this, the final question is, how much time will it take for the driver to reach the runner? The driver's time is really going to be my final answer. So I'm going to make this easier on myself if I just call it X so that I won't have extra work to do at the very end. Now, if the runner left half an hour earlier than the car and they both stop at the same time, the runner is going a total of X plus 1/2 or X plus 0.5. Pen's a little thicker. Let's make those look the same. So half an hour more. Remember that our units are hours. Very important. I cannot say X plus 30. I can't say 30 minutes more because my units have to be hours to stay consistent with that rate, which is in miles per hour. Now that I have the units consistent, I can use the relationship distance equals rate times time. To fill in my distance column, it's going to be rate, which is 10, times time, which is x plus 0.5, and rate, which is 55, times time, which is x. Once I have the table filled in, I'm ready to set up an equation, and the equation is always going to come from the column that has all of the information, which is the last one that I filled in. So I want to think about how these two distances are related. This is where my picture comes into play. We've got a runner in a car leaving the house. We've got a runner in a car meeting up again, right? They are going the exact same path, and therefore they are going the exact same distance. And that is my clue that because these two are the same, I can set them equal to each other. But I really do have to think about it before doing that. That's not how all of these work. In this case, it does make sense to set the two distances equal to each other. And once we have the equation, we have done all of the hard work. We can give our brains a little bit of a rest while we go through the process of solving the equation. So let's go ahead and distribute. 10x plus 0.5 times 10 is 5. I will subtract 10x from both sides just because it looks like this is going to get me to the answer a little quicker. Getting my x's on the right will get me there a little quicker than getting them on the left. And this gives me 5 equals 45x. Divide both sides by 45. And I get 1/9. This rounds to 1/9. So this is x. Let's look back at our definitions here to see that x is a value of time in hours. So this tells us that 1/9 of an hour passes. Well, that could be our answer, but let's look at the instructions one more time. We see that at the very end of this it says round your answer to the nearest minute. If we're going to round to the nearest minute, we first need to express it in minutes. So I'm going to multiply by 60. That is 60 divided by 9 minutes. And in order to round this, I definitely need it as a decimal. So 60 divided by 9 gets me 6.6 repeating. Which finally, as we round that to the nearest minute, we get our final answer, which is 7 minutes. Whew. So this is a little trickier than your average distance, rate, time problem because there was a lot going on. We were given clock times instead of just a description of the relative time each was traveling. Also, we needed to make sure that we thought about everything in terms of hours along the way, but converted it to minutes at the end because we were given some units that were a little bit inconsistent. So a lot to be careful about, I should say, in this particular problem. But the steps involved are fairly typical of any distance, rate, time problem other than that. Generally, one of your columns you'll be able to just fill in directly from information from the problem, right? That would be our rates in this case. So there's usually one super easy one. Then you want to fill in some sort of variable definition next, and you'll have one column remaining at the end for which you need to use the relationship distance equals rate times time. The column you fill in last is the column that you use to set up your equation.